So I'm going to present this experiment that we conducted last summer in Ny-Ålesund. So what we did was we took some kelp that were out in the fjord. We stuffed about 4 kilos of kelp in these giant tanks, which look like bathtubs. And we kept them in these experimental conditions for about 2 months. Does this change? Does this change? Okay. So this is our team. As you can see, this was a very big experiment, so we needed actually all these people, which to coordinate the research question, the experimental design, the logistics of the course, or the experiment, and then people to collect the samples. Which one is these two? That's me and Anise. Anise is going to speak about the task that she led halfway through this presentation. So it took an entire team of researchers and then engineers to actually pull this off and collect some nice experimental data that I'm now going to start to present. But first, just to give you a little bit of representation of where we stand within the FACEIT project. So we are here within WP2 and WP3, still looking at biodiversity changes. So this is going to be specific macroalgal species that we experimented with. And then how these communities in general really kind of might be changing with future climate conditions. And so these two work packages are going to lead right into fueling some of our questions, right? So how are these effects of the future environmental conditions on kelp physiology going to then drive and inform some of these other work packages? So this is really kind of our portion of the FACEIT project within the WP2 and WP3. So to give you a bit of a reference about these experimental conditions that we used. So first was temperature. So this is just showing, this is the IPCC report from 2019. So what you can see here is our color scale of our Arctic in the seasons of March and September. That you can see this is the decadal trend of sea surface temperature increase in red. And so these are different climate change scenarios. So these are different scenarios based on mitigation, if we're able to mitigate or not, or if we're just going to keep burning fossil fuels at the rate that we're doing. But you can see that actually in our fall conditions and then in our early spring conditions or late winter, we still see a very strong increase in units Celsius per decade. So the other driver that we're going to be looking at too is also with this increasing sea surface temperature, and we're going to also experience increasing glacial melt. So this glacial melt, so instead of having the sea terminating glacier, it's actually going to be receding landward. And so we get these proglacial streams and subglacial streams, which are then going to carry a lot of surface sediment and surface detritus that is going to run off and then change our surface light regime and also add fresh water to our system. So with the increase of the glacial melting and then the increase of what we would call turbidity of the water, then we're going to see changes in our light regime as well as our temperature. And so this then gives us our entire experimental suite here. So where we have our future conditions looking at increase of temperature, a decrease in salinity, and then an increase in turbidity, which really just translates to reduced surface light penetration. And so looking at our experimental unit, which is our macroalgae here, our kelp, this was a study that was just released showing that with increasing temperature and some of these other drivers that I was just mentioning, right, sea ice retreat or sea ice presence, temperature, salinity, and nutrients, do we expect to see Arctic kelp actually proliferate into the future? So these are model conditions here. These two different bars are just showing you different artificial intelligence learning algorithms, so they have different sensitivities. You can kind of ignore them, they're about the same, but what we generally see here, so for our subtidal macroalgae, so these are algae that are in the subtidal region, we see a net increase, which is our green habitat gain region here, throughout the Arctic. So we might see some decrease in certain regions, but in general we see an increase within the habitat gain. And so to look at some of the experimental responses, so these are in situ measured and also so laboratory experiments and then also in situ measurements. we can look to see what the responsive kelp are, or macroalgae, to these different stressors here. So this is the effect of the stress, and then you have these different asterisks here, which is either a moderate impact or a strong impact depending on your different region, which you have here. So, for example, unsuitable eroding coastlines with ice, or coasts with little to no sea ice. And what you see here is that for different life stages of the kelp, right? So we have our reproductive stage, our adult or our growing stage, maybe a juvenile stage, and then our adult stage. You can see the effect of temperature, which looks to be mostly positive, increase of turbidity, which appears to be negative, and then salinity we also see potentially a negative response to. And notice that the degree of this impact is really also determined about the habitat that they are actually occupying. So to orient you where we were, so we were in Svalbard here. So in Kongsfjorden, this is an up-close image of Kongsfjorden here. These two green stars are where we sampled our kelp. So we had help from the Avi divers, which were very generous in just, bringing us actually way too much kelp. And we were trying to sort them in our tanks at a very quick pace. So this is the island of Blomstrand, and then this is a site called Hans Nieset, and then this is actually by an old pier, and then our experimental facility was about right here. So these were our tanks. This is what I showed you at the beginning. So we had 12 tanks, and we had 4 different conditions. This was a completely automated setup here. So all these pumps and all these valves that you see here, we're mixing hot water, cold water, and fresh water that was pumped from the fjord at 15-meter depth. And then we had 3 replicates per treatment condition. We have 4 treatment conditions here. So we had an ambient control condition. So this was a dynamic control. So we were actually taking the in-situ measurements in the fjord of temperature, and we were regulating our control conditions to what the fjord was actually reading in real time. And then we applied an offset with temperature, salinity, and then we had a static a decrease or a light filter that went on the top, which simulated the decrease in surface irradiance. So we had our C1 here, which was our moderate condition. So we had decreased salinity, we had decreased light, and increased temperature. We had our more extreme condition, which was higher temperature. So higher temperature increase, lower decrease in salinity, and then even a stronger decrease in surface irradiance or sunlight. And then we just had a temperature condition here. So this was just a high temperature condition compared to our control. And so some of our results, what they look like here. So we ran, what we did in these tanks, let me just back up for a second. So in these tanks, we incubated these kelp so we had about 4 kilos of kelp, as I mentioned, in these tanks for 2 months. And then once a week, we would shut off the flow in these tanks. We would fill up the tanks with the water, and then we would let these kelp, the whole communities, and there are these 4 kilos of kelp, incubate. And inside each one of these, we're measuring temperature, salinity, and oxygen. So we're looking at the oxygen changes to see how much, what the kelp photosynthesis was like. And so these are some of the results what we had here. So we could actually see, so this is our photosynthetic rate on our x-axis. And then these are our different conditions. We had that C0, C1, C2, and C3. And then our x-axis here is just the incoming available light for photosynthesis. And so what you see here is these lines, which if you drew a line through this, right, are linear regression lines. There was really no difference between each one of these conditions. And these were our macroalgal species that we had. So we had Laminaria digitata, Laminaria escalanta, and then Laminaria saccharina. So we can actually construct a model out of this to look to see what the response was to light. So again, if we use these our actual measured data to construct a model, then we can actually see that all these lines kind of overlap. So really reinforcing that it didn't really appear, at least on an hourly photosynthetic rate, that these treatments really differed in their response. So no significant difference in our hourly production. However, if we take all of our rates over the entire experimental period, which was a total of 56 days, And we integrated all of our rates together to maybe get kind of like an estimate of what our seasonal production might look like. Well, then we saw some differences here, right? But we know that there wasn't really any differences here in our short-term production. So is there really a difference in our seasonal production, especially between our C0 and then our most extreme C2 condition? This could purely just be a response to our light, because this had the most decreased light, and that's what we think was actually going on. It looks like the kelp might be a little bit tolerant here, but it's still to be kind of determined, since this was an ex situ experimental study, and we don't really have data of what the kelp metabolism looks like in the fjord. But now to look at the individual species, Anais is going to then present this task that she led. This was a community response. And Anais, I'll go ahead and, oh, I'm sorry, I have one more slide. Okay, so, so what I did then was, since there wasn't really a difference between any of these photosynthetic rates, we can aggregate all these rates, we can pool them together, and we can construct actually a nice model. So this is our photosynthetic rate, again, against all incoming available light. These are all of our hourly photosynthetic rates here. And so we can actually use this then to look at our net community production of mixed kelp communities in the fjord. And so this was the light sensor, or this is the incoming light irradiance over the entire summer period that we had. And then I could plug this into this model here to get our daily net community production rates. And so this is the results of our net community production. But to look to see if there were any individual changes with our species, Anais is going to present what she has. Do you help? You're not supposed to. Okay, well, let's go here.
Thank you. Thank you. So you have been spoiled a little bit already. Now we are going to look at, or if there is a difference in the response of kelp in between the treatment that we used. So here you have the chlorophyll A content, which is the pigment that allows the algae by absorbing light to photosynthesize. So here I plotted the chlorophyll A content of each species. Alaria esculenta, Laminaria digitata, and Saccharina latissima, in between the condition C0, C1, C2, and C3, and also at T0, meaning at the beginning of the experiment. So one first thing that we can note is that for these two species, Laminaria digitata and Saccharina latissima, the chlorophyll A content in between the different conditions is not significantly different in between the conditions. So this is one first observation, but then if you now look at the first species, Alaria esculenta, it seems that for the condition C2 here, the chlorophyll A content remains as high as it was at T0 at the beginning of the experiment. And so here it is quite interesting to see that the C2 condition is actually the condition where we decrease the most the light. So these results could be explained maybe by the hypothesis that this high chlorophyll A content in the low decrease actually, in the low light, sorry, actually compensates for the low light situation. Okay. So if we now look at another result, which is the growth rates. Here you have the centimeter per day, the centimeter per day to which the kelp extends during the whole experiment, so during 2 months in the different conditions, C0, C1, C2, and C3. So you have in purple and in blue Laminaria digitata and Alaria esculenta, and unfortunately you can't really see it. But you can also, let's see, Saccharina latissima in green. And so one first remark is that Saccharina latissima exhibits a much higher growth rate than the two other species. If you don't see it, it's around here. And another important remark is that for the C1 and the C3, sorry, it seems that the range of values are going higher than for the two other conditions, C0 and C2. And one common point in between the C1 and C3 is that for both treatment we increase the temperature. But actually it's also the case for C2. We also increase the temperature in C2, it's written here. But here in C2 we also decrease salinity and decrease light. So one hypothesis that could explain the result that we have here is that warmer water could enhance the growth rate of some individual of Saccharina latissima, but the hyposalinity and the low light might inhibit this positive effect on the growth rate. So to conclude, we saw that Alaria esculenta might be advantaged in low light. Actually, studies found that it's one or the only species that extend in depth and is actually extending, while most kelp species are actually going less deep. I mean, their vertical extension is going more in the surface, and therefore this species might be more dominant in depth in the future. For Saccharina, what we found therefore is that it exhibits a higher growth rate, and therefore it might exhibit a higher biomass, especially offshore when you have warmer waters but no low light and no hyposalinity conditions that are induced with the melting of the cryosphere. But this actually has to be taken carefully, since we also have to look at other parameters and other life stages. And for the third species, Laminaria digitata, we actually found no effects of the treatment that we used on the species, meaning that the species might continue its development, but as you understood, there are other species that might exhibit a potential competition, and therefore the species might face other species sometimes more competitive.
Okay, and just to wrap up what we have here, so some of our summary conclusions. So short-term production for the mixed kelp communities here, they appear not to be necessarily affected by climate change, at least negatively, as we saw mostly homogeneous photosynthetic rates across all of our treatment conditions. However, seasonal production remains a little bit of a mystery. So there could be maybe a small change to our most extreme climate condition in our seasonal production. It's very hard to tell though out of a 2-month experiment where we were doing incubations once a week. And then, as Anais just said, so our mixed kelp communities we may undergo shifts in what dominant species are actually present in these mixed kelp communities. And so finally, we can use these estimates of the community metabolism, which can provide insight into things like carbon and nutrient cycles that are relevant for biodiversity and ecosystem functioning. And to bring it all together, why do we even care? Sorry, this is cut off the top here. This is a little bit too big. So why do we care, right? So because kelp communities in general, they provide a baseline ecosystem. And so this can have positive effects on biodiversity, nutrient sequestration, oxygen provision, and the habitat. And then these then have ancillary effects for all these other things that our work packages are investigating, our colleagues here. So things like tourism, the coastal assets, and the socioeconomic products that the human communities actually rely on. Our goal now with the rest of this FACEIT meeting is to actually integrate our results from work package 2 and 3, as we were talking about, and what we just heard in this previous lecture right before the break, about making sure that our research results actually move into the adaptive behavior for these other work packages. And with that, I want to thank everybody, and thank Anais for your presentation, part 2, and we'll take questions if we have time.
Thank you very much for this interesting talk, and I think I have lived so long in Svalbard that I've seen a massive increase in
the kelp in the intertidal zone, and the saccharina is really increasing. So very nice. Is there any questions for these two people? Yeah, and I can throw this. Looks so fun. Ooh, yeah.
Wow. Hello, thank you for your really interesting talk, and it matches also some of the things that we found last year. And I wanted to ask, so you said you have 4 kilograms of kelp in each tank, and I was wondering, was it like, so you had like 3, so 1 specimen of each species in each tank, or how was the, yeah, what kind of, what was the community like that you had in the tanks?
So we used literature values to look at what the each kelp species was in a meter square area. So and we did this according to biomass. So I think, for example, we had like maybe 1,500 grams of one species, 2,000 grams of another, to having a total in this 1 meter or meter squared plot to be about 4 kilos of kelp in general.
Thank you.
Mm-hmm.